Everybody, JC Coffee here, and today we are going to talk about some exciting information about artificial intelligence and the way that we can utilize it to help in our everyday life. So we're going to hear from Thomas Hartung, and he's going to talk about organoid intelligence. So let's get started.
Here to the stage. He is a toxicologist interested in replacing animal testing with much better methods. And now the floor is yours.
Yes, indeed. My quest is to make us less reliant on animal experiments, which the type of you just heard. And we are embracing all types of technologies to do so. This includes advanced cell culture and, for the last 10 years, artificial intelligence. So we started to use artificial intelligence for predicting properties of chemicals, for making sense of omics data, and so on. Today I want to show you how these two get together in a type of organoid intelligence. I'm talking also from the perspective of the field chief editor of Frontiers in Artificial Intelligence. We created this journal over the last 4 to 5 years. We have published more than 800 articles in all areas of artificial intelligence use. And I don't need to tell you after today's workshop how much this technology is exploding, simply because we have a synergy of 3 trends. One is data formation. We have a stable increase of data by 60 to 70% per year. Or another way said, more than 90% of all data in the world were produced in the last 3 years. Computers are growing in capacity over the last 60 years, known as Moore's Law, twice every second year at half the price, which means 40% increase per year. But AI, for the last 12 years, has been doubling in its capacities every 3 months, which means that altogether, we have seen a 1 billion-fold increase in computational power towards artificial intelligence in the last 60 years. And this is why suddenly we are seeing it popping up essentially everywhere. And this reminds of R.E.M.'s famous song, "It's the end of the world as we know it," and importantly, "and I feel fine." And I will show you why I feel fine in the remainder of the talk. Because of my role as field chief editor, I had the possibility to help drafting the World Economics Forum transformational map, Artificial Intelligence Facilitated Healthcare. Because all of healthcare, and we are talking here of 10 to 17% of the GDP of modern countries, is transforming at the moment on the ground of AI. It is dramatic what is happening, not only in the few disciplines we touched on today. And a shameless plug, if you're interested in more, I'm organizing with my 2 colleagues here a Keystone Symposium, a virtual Keystone Symposium early May next year, which will be virtual and accessible over these 3 days. Okay. What we see at the moment is that this exponential growth in the capabilities of AI allows us a tremendous assumption and emulation of human skills. What you can see here is that it took us more than 20 years until AI was capable of learning human handwriting. But now, most likely, we see that things like coding is something AI can take over in less than 2 years. Last year, about 40% of all coding was done by AI. And it's calculated that this year, 80% is done by AI. While coders were a rare commodity about 2 years ago, they were laid off in large proportions last fall when the tech industry freed itself of superfluous work capacities. And this is also capacities such as the passing of a bar exam for lawyers. While this was at about 10% with GPT 3.5 a year ago, GPT-4 this year was performing at the 90th percentile of a human. So this is showing you how fast suddenly human skills get accessible. There's 2 technologies which are disrupting, from my point of view at the moment, the way we do biomedical research. One of them is microphysiological systems. The other one, obviously, is AI. Microphysiological systems is a type of advanced cell culture. We have to say that until quite recently, it was very difficult to build cellular models of human cells. Because if you're not working on blood or skin, it is very difficult to get human cells. I'm working on brain. It is very difficult to pick a brain of a human, except at the rare cases of surgery. And this is typically an old person or at least a diseased person. And I get tiny quantities and never the same material again. Tumor cell lines are not organs, not humans. So we really needed something which is based on stem cells. And especially with the ethically less problematic induced pluripotent stem cells, only invented in 2006. We have now access to grow essentially any organ. And this has given rise to so-called microphysiological systems, which is organoids and organ-on-chip systems, which are characterized by showing an aspect of architecture and of functionality of the respective organs. We have done several workshops in order to promote this community. The last one led to this science paper on human microphysiological systems for drug development, which I invite you to read if you're interested to get an overview. We also started a series of world summits and created an international society for microphysiological systems, and we will meet the next time in Seattle in June of next year. So this is an exciting form of bioengineering and its users coming together. And in Berlin this year, we had to close 6 months in advance because we reached capacity at 1,300 people, and we had a waiting list of sponsors for a conference, which I've never seen before. Okay, in my field of the brain, it is important to note that Vienna is one of the birthplace, or a hallmark at least, on the way towards brain organoids, where the Knoblich group here developed in 2013 the first induced pluripotent stem cell-derived brain organoid as published in Nature. We published our first work on brain organoids the same year, and in 2016 we were able to report on the mass production of brain organoids, which are tiny and small, but they are equal in composition. They're not as big as these ones, these beautiful ones you see up here, which however are having problems of access to oxygen and nutrients in the center and are accumulating some dead cells. The Financial Times on its front page titled "Mass-produced mini brains to spark rethink over drug testing on animals." So that was dream achieved. Since then we have been using it actually in autism research. We used them to be the first in May of 2020 to show that COVID-19 is infecting human neurons. We grafted them with glioblastoma and a lot of other research. But this is not interesting for today. My wife, leading this research in our team, has active work on Alzheimer's, on autism, on various virus infections and others. When we started, we showed some of these pictures, and I hope you can see here sometimes a little yellow flash. This is a neuron which is depolarizing, shown by calcium fluxes. And I very easy said on this, yeah, they are thinking. They spontaneously are showing these type of behaviors. And then some people were shocked. They say, are they conscious? And I said, no problem. They have nothing to think about. They don't have input and output, which is certainly a good line of defense against the attack of this could be a conscious system. But it was also something which intrigued me to suggest, couldn't we do something and start communicating with them? Like today, many people started to talk to animals through AI. Can we talk to brain organoid? Can we combine AI with an organoid? And this is exactly what we have been doing over the last 3 years. So the idea is to create organoid intelligence, OI, as a synthetic biological AI. So just the opposite of what computer development has been doing, which is to make a computer more and more like a brain, ultimately artificial intelligence. We try to make a brain organoid culture more computer-like. Can it process information? Can it learn and memorize? And this is quite interesting because the brain is a damn good computer. This is the, I think, still fastest supercomputer in the world, the Oak Ridge National Laboratory Frontier supercomputer in Kentucky. It achieved 1.1 exaflops of computational power in June of last year at a 680 square meter installation, which did cost $600 million. Interestingly, 1 exaflop is the estimated computational power of a single brain.
Wow.
So you see the difference in dimensions. Yeah? So we do with 1.4 kilogram essentially as much computation as a supercomputer. Or you can say it a different way. If you look into a laptop, a modern laptop, it would take another 33 years of Moore's law until our laptops are as capable as a single human brain. And interestingly, the supercomputer needs about 1 million times more energy as the two, a laptop or a human brain. This shows you that there's at least theoretically potential for a different way of computing, either by just assuming some of the architectural and algorithmic solutions of the human brain, or possibly even by implementing some type of a biological unit within the computer system. So the idea of OI is that the organoid is linked to AI and is getting input and output and very important feedback on its output. And this could open up for quite a few things. It could first of all allow us to understand the physiology of learning in a human cell system. So if we can demonstrate that these systems are learning and memorizing things, we could start interrupting, we could start to use all our pharmacological tools, our genetic tools, and we could start imaging of these processes. We could start to use them as brain-machine interfaces. We have heard today a lot about brain-machine interfaces, but before you go into humans, you typically go into animal experiments. It would be very interesting to see how human materials are interacting with these electrodes, the different materials, and so on. For me, as a toxicologist and pharmacologist, it is most interesting to find systems for drug development, let's say in Alzheimer's disease, or to understand why are diseases like autism exploding, Now 1 in 36 children in the US is diagnosed with autism. We were at 1 in 10,000 in the 70s. Is there a chemical contribution? Is there a contribution of chemicals to Alzheimer? Because Alzheimer is increasing more than the aging of the population would actually suggest. But nobody has a tool to identify possible contributions. And then, especially computer engineers are dreaming to learn how to do better computers, possibly use this. So already two-dimensional cultures of human neurons, so flat things, not the brain organoids, pure neurons typically, are doing quite amazing things. Our partners from Cortical Lab last year, in November, published this paper, which they called a dish brain system, and they showed that this system is actually learning to play the computer game Pong. So this pedal here is controlled by a neuronal culture, and they quite convincingly show that this system is trainable. It gets better in a 40-minute exercise. And this is, I think, a very important step forward to use such a virtual environment to benchmark the learning capacity of such a neuronal system. Interestingly, and as we pointed out also in our editorial, which Lena and myself wrote to accompany this article, this system is forgetting everything in a day. So next day, there's no memory of the training, it starts from scratch and has to learn again. And that's clear because it does not have the machinery for long-term learning, because it has no glial cells for pruning the connections, the synapses, to strengthen the connections which are learning related, and for this reason they don't have. And for this reason, Cortical Labs and we collaborate. They're now using brain organoids we produce, and we're doing the same thing in Hopkins. So these brain organoids, they're only 0.5 millimeter, they only have about 50 to 100,000 neurons. They have, from what we know, all of the architecture and physiology for cognition. They also have another number of advantages. They have about 1,000 times higher cell density, which allows many more connections between these neurons, because cells are in proximity to each other. They have myelination. We have just published this week a paper that we are also able to raise the glial cells to the physiological about 50% content, and about 40% of all axons are myelinated, which allows conductivity of the axons of the electrical signals to increase by about 100-fold. So this is a system which should be capable of doing learning. Now we need the electrophysiology side. A year ago already, we published on this system, which is shell electrodes. And these shell electrodes are, as you can see, embracing the brain organoid here and allowing something like an EEG in a human, so a much better signal-noise ratio and a spatial recording. And then you can start adding some type of pharmacological agents like glutamate, and then you see the change in the spontaneous reactivity of these. So that's a starting point. However, this is probably a system too small, as I said, about the number of neurons of a housefly. You don't want to train this on playing a computer game as much as you don't want to have your fruit flies or houseflies play your computer games against you. Some funding from Johns Hopkins enables us at the moment to go on scale. We're developing brain organoids which are about 1 centimeter in size, which is already twice the size of a mouse brain. And in close collaboration with the Applied Physics Laboratories, which is one of the powerhouses of Hopkins, and importantly, ethicists of the Behrman Institute of Bioethics in Hopkins, we are creating more and more virtual environments, including maze systems similar to the animal experiments, where we try, is a system trainable here? And we are about to connect to some of the robots in the Applied Physics Laboratory to understand whether we also can do more than just virtual environments. This shows that we are suddenly entering a field where intelligence, and want to be very clear, the term has no consensus, not in humans, not in animals, and certainly not in the overlay. And we have certainly a need for different type of definitions for what intelligence means when we are then bringing in either artificial intelligence or organoid intelligence in the future. We are certainly only talking about the very basic questions of memory and learning. You should not expect for the foreseeable future to come to our lab and talk to a brain organoid. It is really about very, very simple tasks, but the fundamentals of these. This opens up for a lot of ethical questions. Nature has titled already in 2020, Can Lab-Grown Brains Become Conscious? So for us, it is very important that we have quite a number of ethicists on board since we started these projects, and we have agreed on a process which we call embedded ethics, which means every week when we meet to discuss our progress, we have ethicists on the call. They come to our labs, and their expectations get quite humble when they see these little snowflakes of brain organoids, and they understand that at the moment there's certainly no risk of something becoming conscious. But we want to anticipate possible discussions, and for example, they are serving a general public of who has concern and where does it get, this should better not be done, to understand how people react to this. And it is also opening up for something which is experimental ethics. You can start to define what is learning, memory, consciousness, awareness in such a system. Then you can see what does it take. How big does the system have to be? What is the type of input you need to generate something like this? Could there be any type of rudimentary pain or suffering in the absence of nociceptors, of pain receptors, and so on and so on. So we're discussing this, and one of the colleagues already is setting up his career in experimental ethics, which I think is most interesting. As I said, for me, one of the goals is to replace animal testing, for example, in Alzheimer research, and we have teamed up with the Alzheimer Institute in Hopkins. Interestingly, if you take induced pluripotent stem cells from Alzheimer patients, the cells, the brain cells you can generate, show aspects of histopathology of Alzheimer patients. Some of the things which go wrong in Alzheimer patients. And now the idea is, this response to this training, we want now to see, is this different in a brain organoid which is derived from Alzheimer cells. We're not only studying Alzheimer, we're also working on amyotrophic lateral sclerosis, we work on autism, we work on some rare diseases which involve cognitive deficits, leukodystrophies, SYNGAP, and others, because once you have the technology,